Okay, good morning, everyone. So today we are going to talk about the gas laws and we'll do some problems related to these gas laws. So in topics that I'm going to, if I list the topics that we are going to cover today, will be the first we'll start with the Boyle's law, then we'll cover the Charles and Gay-Lussac's law, then we'll move to Avogadro laws and um, I'm going to connect all these, combine all three laws, and we'll learn about the combined gas law. And after we learn about all these gas laws, I'll finish the lecture with the ideal gas law equation. Okay, right. Let's move on. So, what is the Boyle's law? The Boyle's law say the pressure, a volume or pressure or volume. Okay, if I would just stay with this equation, the volume of a gas sample is inversely proportional to the pressure of it at constant temperatures. So the volume of a gas sample is inversely proportional to the pressure of it. What does it mean? Okay, when you look at a graph like this, if you are increasing the volume of a gas sample, that will decrease its pressure. That what is said by this Boyle's law. So you will see now we are increasing the volume, then you will see it is decreasing the pressure. Okay. So when the volume is 40, okay, as an example, when the volume is 50, the pressure is 1500 mercury millimeters. But if I increase the volume, okay, to about 55, then the pressure has been decreased up to about 1450 mercury millimeters. So when we increase the volume, the pressure will decrease at constant temperatures of a gas sample. So then we'll put a constant, and then the proportionality sign will become an equal sign. So the volume of the gas sample equals the constant 1 over P, that is made by inversely proportional. So if I just reorganize this equation, solving for the constant, then I would say PV equals K. Pressure multiplied by volume equals to a constant at constant temperature. So, if I just look at a same gas sample at two different at constant temperatures, okay, a same gas sample at constant temperatures, but with different pressure and volume combination. So I would say P1 V1 equals K1, even if I do not change the temperature, then again for any combination of the pressure and volume, multiplication of pressure and volume equals to that same constant as long as you do not change the temperature. So we can come up with a new equation which relates the combinations of different pressures and volume combinations at constant temperature as P1 V1 equals P2 V2. You can apply this equation at only constant temperature. If the problem says the temperature has been changed, then you cannot use this Boyle's law equation. The Boyle's law equation can be used at only constant temperatures. What is that equation? P1 V1 equals P2 V2. So what does Boyle's law say? The Boyle's law say the volume of a gas sample is inversely volume of a gas sample is inversely proportional to pressure. So we can apply a constant. So this PV equals to a constant at constant temperature. Let's use this Boyle's law to solve this problem. If a skin driver takes a breath at the surface, filling his lungs with at the surface, filling his lungs with 5.82 liters of air. What volume will the air in his lungs occupy when he dives to a depth where the pressure is 1.92 atm? Assume constant temperature and that the pressure at surface is exactly 1 atm. Okay, we are asked to assume that these two condition scenarios happen at constant temperatures, and we are given the pressure at surface as 1 atm. So P1 equals pressure 1 equals 1.00 atm, and the volume, the 1 equals 5.82 liters, and the second pressure is given as 1.92 atm, and we are looking for what? Yes, we are looking for V2. So we'll use the Boyle's law equation. P1 V1 equals P2 V2. Now we want to solve for V2, so we rearrange this equation. Then P1 V1 equals P1 V1 multiplied by P2 will equal to V2. Okay. Now you just need to substitute the numerical values for these abbreviations, and you need to solve this and get the answer for V2. Do you need a 1 minute to solve this problem? Okay, we'll plug these values. P1 equals 1.00 atm multiplied by the volume 1, which is 5.82 liters, and divided by the pressure 2, it is 1.92 atm. Okay, keep this in mind. The pressure values should be in a one type of unit. As an example, in this question, P1 and P2 are both in ATM units. You cannot substitute the pressure, any pressure or volumes in two different types of units. They should be in the same format, and the V1 is 5.82 liters divided by the P2, it is 1.92 atm, and it was solved and got the answer as 3.03 liters. Then next, let's look at the sig figs. Every number has three significant figures, so we'll give the final answers with three significant figures. Let's move on. Now we are moving to the Charles law. It relates the temperature and volume. It relates the temperature and volume of a gas sample. The Charles law say the at constant pressures, the volume of a gas sample is directly proportional to the temperature. Look, I am increasing the volume from 1000 to 1500. And as well, the temperature has also been increased. So the volume of a gas sample is directly proportional to the temperature of that and temperature of a gas sample. This graph is done using different gases, but you still see that the direct relationship at constant pressures. So we can say V equals, first it was like this, V directly proportional to the temperature. Now we'll add a constant and a constant pressure so that we can just take it as K subscripted 2. So V then equals to K2 multiplied by the temperature. If I rearrange this equation, V divided by T equals K2. So, if we consider the two different volumes and two different temperatures, but under constant pressure, that constant will be same. The relationship between the volumes and the temperatures at for two different combinations, if you do not change the pressure, then that constant will be same. So like in Boyle's equation, we can come up with a new equation which relates two set of parameters, two set of conditions. So under constant pressure, it is V1 over T1 equals V2 over T2. And all these temperatures should be plugged in or should be given in Kelvin temperatures. You cannot apply these temperatures in degrees of Celsius. You need to plug all these temperatures in Kelvins. V1 over T1 equals V2 over T2. And when here is another example. A sample of argon gas that originally occupied 14.6 liters at 25 degrees of Celsius was heated to 50.0 degrees of Celsius at constant pressure. What is its new volume? Okay, so this the data has been collected under constant pressure. So then this is related to the Charles law. Okay. So what is the equation we derived from the Charles law? Yes, it is V1 over T1 equals V2 over T2. And remember, we can plug the temperatures only in kelvins. Therefore, we need to change these temperatures to Kelvin temperatures first. Do you remember that how you can change a degrees of Celsius to Kelvin? Yes, you will add 273.15 Kelvin to any degrees of temperature in degrees of Celsius. Okay, good. So when I added and when I converted the temperatures in Celsius to Kelvin, I got the temperature 1 as 298.15 Kelvin and the second temperature as 323.15 Kelvin. The volume 1 is given as 14.6 liters. So I am looking for the V2. So if I rearrange this equation for the V2, then it is V1. The T2 goes to the numerator. V1 multiplied by T2 divided by T1 will equals to the V2. Okay, so now I'll plug these numbers for these abbreviated terms and solve, and I got the answer as 15.8 liters as the new volume under 50 degrees of Celsius or under 323.15 Kelvin. So what you need to remember with this Charles law? Yes, the equation is V1 over T1 equals V2 over T2, and you can apply it under only constant pressures, and you need to plug the temperatures in Kelvin values, Kelvin numbers, Kelvin units. Next, we'll look at the Avogadro's law. And Avogadro's law relate the amount and the volume. The amount is the moles and the volume is V. Under constant temperature and pressure, okay, the volume is directly proportional to the amount. So under constant temperatures and pressures, we can say V equals the constant multiplied by the amount. So if I solve for the constant, then it would be V1 over N1. Right, V over N. And okay, under constant temperatures and pressures, for the same gas sample under two different set of conditions for volumes and amounts, then the relationship between these volumes and amounts will be equals to the same value, since we have not changed the temperature and the pressure. So then we'll get this relationship uh, V1 over N1 equals V2 over N2. Okay, right. So let's move. Let me explain it further. Look at this stoichiometry, the equation. The first you need to check whether it is balanced. 3H2 gas is allowed to react with 1 mole of N2 gas and gives 2 moles of ammonia, NH3 gas. Okay, from the stoichiometry, what we have learned in our last chapter, okay, we know we can relate the different the compound substituents, the amounts of substituents by the stoichiometric ratio that we obtain from a balanced chemical equation. So I would say then 3 molecules plus 1 molecules give 2 molecules of ammonia, or 3 moles of hydrogen plus 1 mole of nitrogen gives 2 mole of ammonia. Now, with the Avogadro law, if the temperature and the pressure have not been changed, if those two are constant, if the pressure and the temperature is constant, then I could say 3 volumes plus 1 volume equals to gives 2 volumes of ammonia. Remember, we derived a relationship between the volumes using the same stoichiometric ratio. If the reaction if the reaction was carried out under constant pressures and the constant temperature conditions. Look at this example. If we combine 3.0 liters of nitrogen oxide and 1.5 liters of oxygen, and they react according to the balanced equation, 2NO gas plus O2 gas gives 2NO2 gas. What volume of NO2 will be produced? Assume that the reactants and product are all at the same temperature and pressure. Good. Apply Avogadro's law to determine the volume of a gaseous product. Now we are given the volume of NO, the volume of O2, and we need to find the volume of NO2. And we were told that all the reactants and the products are in the same temperature and the pressure condition. So we can use the Avogadro's law to find the volume of this product. Okay, so what is the balanced chemical equation? 2 to 1 and 2. Okay, if I use two volumes of NO, I'll get one volume of O2 and two volumes of NO2. So, what are the numbers? 3 moles of NO, 3 zero point 0 liters and 1.05 liters. And what is the volume of the NO2 will be produced? Yes, it would be 3.0 liters. We obtain it from the balanced chemical equation. Next, now I am going to combine all three um, gas law equations what we have learned so far. Boyle's equation, Charles' equation, and the Avogadro's equation. And combining all these three, I'll get this equation. P1 V1 over N1 T1 equals P2 V2 over N2 and T2. If I apply this equation for a fixed amount of gas, I am not changing the amount of gas, then this N1 will be equal to N2 and I'll get this equation. P1 V1 over T1 equals P2 V2 over T2. We call this one as the combined gas law equation. Combined gas law equation. Okay. Now look at this problem. If a child releases a 6.25 liter helium balloon in the parking lot of an amusement park where the temperature is 28.50 degrees of Celsius and the air pressure is 757.2 mercury millimeters. What will the volume of the balloon be when it has risen to an altitude where the temperature is negative 34.35 degrees of Celsius and the, the air pressure is 366.4 mercury millimeters? Okay, we are looking for a volume. Okay, so we are given the V1, volume 1, and the temperature 1, T1, and we are given the P1. And we are looking for the V2 and we are given the T2 and the P2. What is the other thing? Yes, we can only apply the temperatures in only Kelvins. So you need to add 273.15 Kelvin to degrees of Celsius to change these numbers to the units in Kelvin. So I found the temperature 1 as 301.65 kelvins and the temperature 2 as 238.80 kelvins. So I have three parameters: pressure, volume and temperature. So I'll be able to use that combined gas law equation. P1 V1 over T1 equals P2 V2 over T2. Okay. Now you are looking for this V2. So if I rearrange this equation, V2 will be equals to P1 multiplied by T2 multiplied by V1 divided by P2 and T multiplied by T1. Let's plug these numbers and remember I just want to highlight all the pressures are in the same type of unit and the temperatures must be in kelvins and the volume is applied in liters, so I'll obtain the answer for the V2 in liters. Okay, so now I have finished all three gas law equations and the combined gas law equation. I am moving to the ideal gas law equation. Okay, right. So we talk about the Boyle's law. We now we know that the pressure of a gas sample is inversely proportional to its pressure, and according to the Charles law, the volume is directly proportional to the temperature, and from the Avogadro's law, we obtain that the volume is directly proportional to the amount. So now I relate that the volume is directly proportional to the N, that the amount, multiplied by the temperature in Kelvin divided by the pressure. So this is a proportionality sign. So how we can remove this proportionality sign? Yes, we need to apply a constant. Yes, I put a constant that is known as R, that is the ideal gas law constant. Okay, so V equals R N T over P. But this equation will be rearranged for an easier format, and it is PV equals nRT. That is the ideal gas law equation. PV equals nRT. Okay, the value for that ideal gas constant can be given in uh, different types of units. If it is the liters multiplied by ATM kilo, okay, let me use this. PV equals nRT. Okay. If I solve for R, okay, I am trying to get the units for the ideal gas law constant. Then it is PV divided by NT, right? So if the pressure is applied in ATM and the volume applied in liters, and the amount always it should be applied in Kelvin, and the temperature should be always applied in Kelvin, then the numerical value for the R is 0.08206. But if I look, sometimes it can be given as 8.314, then the R will have the units as joules over Kelvin multiplied by moles. Like we most of the time we'll work with this unit, but when you move to the 152 or the general chemistry 2, there you are going to learn about the equilibriums and uh, the rate law equations and the energies, the thermodynamics. Then you will use this value. So, the ideal gas law equation, okay? If it is using the ideal gas law equation, we can relate it to all other forms. As an example, when the volume of 1 mole of an ideal gas at 0 degrees of Celsius and 1 atm conditions, we call these conditions as standard temperature and pressure conditions. When the volume um, one amount is 1 mole, the temperature is 0 degrees of Celsius, and the pressure is 1 atm. Those are standard temperature and pressure conditions. Then what is the volume? We'll plug these answers, okay? 1 mole, the constant is 0.08206 liters times atm divided by K times moles, and the temperature is 0 degrees of Celsius. So, which is in Kelvin, it is 273.15 Kelvin, divided by the pressure, it is 1 atm. Oh, the volume for a for any for any gas sample. It doesn't matter whether it is oxygen or whether it is nitrogen or hydrochloric or whatever. If when we apply this ideal gas equation, if we assume all these gases behave as an ideal gas, then the volume of this gas sample for any gas sample at standard temperature and pressure conditions. What are these standard temperature and pressure conditions? Yes, the volume of a 1 mole of an ideal gas at 0 degrees of Celsius and 1 atm is 22.41 liters. Okay. So based on that, now we need to find the volume of a mole of an ideal gas at temperature 25 degrees of Celsius and 1 atm. So according to the data, we know the amount is 1 mole. Temperature is now changed to the Kelvin, 298.15 Kelvin, and the pressure is 1 atm. And we use because the pressure is expressed in atmosphere units, we need to use this the value for the gas constant. It is 0.08206 liters multiplied by atm and divided by K and mole to solve for the volume in liters. Okay, when I plugged these numbers and I found the answer as 24.5 liters for the volume. Now we can apply the gas law equation um, for uh, for different types of conditions. As an example, we can find the molar mass, or we can find the density, or we can find the mass of a gas sample. What? How we can do that? Let's rearrange this equation like this. What is our gas law equation? PV equals nRT. You can play a lot with this gas law equation. That's what I said. This is very important one. The ideal gas law equation. You can do tons of things with this gas law equation. So when I rearrange this equation as an N over V equals P over RT, then I'm going to multiply the both sides by the molar mass. What is M multiplied by N? Molar mass multiplied by N. Yes, that is the mass. What is mass divided by the volume? Yes, that's the density. So then the other side, where the right side of this equation will be pressure multiplied by the molar mass divided by the gas constant multiplied by the temperature. So using this equation, you can calculate the density of a equation. Or if you know the any the density and the amount and the volume, you can find the molar mass even. Okay, from a gas law equation. How you can find the molar mass? Yes, PV equals nRT. Okay, then I would say PV equals what is moles? Yes, that is the mass divided by the molar mass RT. So when I solve for the molar mass, then mass multiplied by the gas constant multiplied by the temperature in Kelvin divided by the pressure and the volume. You can calculate the molar mass of an unknown substance if you know the mass of that sample, if you know the gas constant, if you know the temperature, and if you know the pressure and the volume. Look at this example. The carbon dioxide is effective in fire extinguishers partly because its density is greater than that of air. So, carbon dioxide can smother the flames by depriving them of oxygen. Air, air has a density of approximately 1.2 grams per liter at room temperature and 180. Calculate the density of carbon dioxide CO2 at room temperature 25 degrees of Celsius and 1.0 atm. The molar mass of carbon dioxide is 44.01 grams per mole. We are looking for the density of the carbon dioxide. We are given the molar mass, we are given the temperature, okay, and we are given the pressure. Right. Okay. So we'll use this equation. Density equals P multiplied by the molar mass divided by the gas constant multiplied by the temperature. Pressure is 1 atm. The molar mass is 44.01 grams per moles. The gas constant is 0.08206 liters. ATM divided by K Kelvin multiplied by moles multiplied by 298.15 Kelvin. So when you solve this, you will get the answer in grams per liters and the density is 1.8 for this carbon dioxide. Okay, like that. You can use this ideal gas law equation to calculate the density. Okay. So the you can now relate this gas law equation to solve the properties of a gas component in a balanced chemical reaction. So how you can do that? Um, Look, when you are calculating the required volume of a gaseous reactant, then you can use that Avogadro law. Okay, so you can relate the moles and uh, with the volume. Okay, so it'll be easier to calculate the required volume of a gas constant if the pressure and the temperature are kept constant. Right. Then next, you can calculate the required volume of a gas constant, even like this. When the substance are in two different physical states. Remember the previous equation, all these components should be in gas phase. Then you can simply relate the amounts and the volumes. When you need to relate the amounts with the volume, then every component should be in gas phase. Okay, but look at a condition like this. Now, two of these components are in solid form and one component in gas. Then how we can solve it? Yes, then we can start with grams of sodium. Then we change it to moles of sodium. Using the balanced chemical equation, we can get the moles of Cl2. We got this combination from the that's the stoichiometry relationship. We obtain it from the balanced chemical equation. Now we need to change the volume of Cl2 to the moles of Cl2 to its volume. Then who comes to help us? Yes, this ideal gas law equation. The PV equals nRT. Okay, PV equals nRT. Okay, so we know the R, we will be able to find the volume if we know the pressure and the temperature. Good. Yeah. So like this, you can do lots of calculations with this gas law equation. That's all I'm going to cover today under gas law and calculations review.